So a problem you'll encounter early on in a calculus class is the derivative of sine and cosine. In these classes you will usually use a limit definition to prove them, but today we're going to be using a geometric proof. We're going to be considering this satellite orbiting a planet. It will be orbiting a distance 1 from the planet, and we're going to say it's moving at its speed of 1, which means that if we let it go, it will move a distance of 1 for 1 unit of time. Now, what we're using as the unit of time is the angle the satellite makes with the x-axis, this angle here. And so this is going to rotate perfectly in time. And so the positioning of the satellite at any point is going to be cosine of t in the x direction, where t is both the time and the angle, and the sine of t over here. So let's say the planet that the satellite was orbiting vanishes, and so the satellite can only drift into free space. It will be moving will move a distance tangent to the circle, and let's consider only for a change of time of 1 time. In 1 time, it will have moved a distance of 1 tangent to wherever it was on the circle at that time. Now it will have moved some distance up, change in y, and some distance to the left. We're going to call change in x. So the angle that the radius and the tangent line makes is actually a right angle. And so we can actually find out what the angles within this triangle are. Well, we know that one because it's a right triangle. It's because the change in y and the change in x are going to be perpendicular. And because this is the complement of t, this is a degree of pi over 2, and the angle that these two verticals make are an angle of pi, this angle has to be t. And so this angle is pi over 2 minus t. And we can see that these two triangles are actually congruent there because of side, angle, side, or angle, side, angle, and then angle, side, angle. So let's find the speed in the y direction of our satellite. We're going to be looking for dy dt. It's going to actually be exactly equal to change in y over the change in t, because once the satellite's released, it's going to be following a constant velocity because no other force is going to be pulling it back in. And so, because the change in time is 1, this is just equal to the change in y. Now, these two triangles are exactly congruent, so we can say the change in y is equal to cosine of t because they're across the same angle, pi over 2 minus t. And so we can say the change of y is equal to cosine t. Now let's look at dy dt again. Y is going to be sine of t, because sine of t gives the y position of the satellite. So all this is saying is that the time derivative of sine t is equal to cosine of t. And that is indeed the derivative of sine. And so we can do this also for cosine if we consider the rate of change of x, dx dt. This is actually going to be equal to minus change of x because the x goes to the left, which is negative. And so this is going to be equal to minus change of x, which is equivalent to the side across from t, or sine t, or in other words, the derivative in terms of t of cosine of t, which is x, is equal to minus sine t. And so those are the derivatives of the sine and cosine with a geometric interpretation.